All right. So we're talking about this paired data, match pairs test. Let's look at an example. Is the express lane faster? So for their second semester project in stats, Libby and Catherine decided to investigate which line was faster at the local supermarket, the express lane or the regular lane. To collect their data, they randomly selected 15 different times during the week. They went to the same store, bought the same item. One of the students used the express lane and the other used the closest regular lane. To decide which lane each of them would use, they flipped a coin. They entered the lanes at the same time, paid with the same method, and recorded the time in seconds it took to complete their checkout. So again, you see two lists. So it's, if kids aren't thinking, they just run a two-sample test because you got two lists, two samples. They're going to test whether mu1 minus mu2 is, if there's a difference, right? But remember, both the second and the third, all of these conditions are dependent upon having independent samples, right? Yes, this is sometimes this two-sample test is called a two independent sample test, right? These are not independent. These are linked. These are dependent on each other. This is the same time, the same item right next to each other. So this is paired data. So what we're going to do is we're going to calculate a difference list. We're going to look at these differences, one minus the other, and then we're going to do a one sample procedure or a paired t-test on the difference list. Okay? Call the differences D if you want. That's why we had D bar when we took the mean of it. Okay. Carry out a test to see if there's convincing evidence that the express lane is on average faster. So, mu D is going to be the mean, X bar. Mu D is going to be the true population mean of the differences in wait times, regular express minus express at all possible times at this store. So our kind of sample, our population of interest is all the different times we could go to this store. And this would be the true mean of the differences, the mean of all the differences. So it would be the mean of this infinite unknown list. So the null hypothesis is that there's no difference. So my differences would be equal to 0 if there was no difference. So the null hypothesis is that mu D is equal to 0. The alternate is that mu D is greater than 0. If I think the express lane is faster, is the express lane faster on average, then the express lane time to checkout should be less, and this difference should be greater than 0. So I'm testing the alternate that mu D is greater than 0. Check the conditions. I did do sampling. I sampled the times, so the times were randomly selected. The 15 times were randomly selected. 10% condition, 15 times or less than 10% of all possible times. I could go to the store, any one of hundreds or thousands of times. Now, to check the third condition, my sample size is small, so I can't use the large sample. I can't use the central limit theorem. So I need to look at my data. Let me pause this and pull this up on my calculator. Maybe you want to type this in and follow along. I don't know. Okay, so again, if you want to follow along, maybe you can pause and put this into your calculator in two lists. I've already done that, so I'm going to take it from here. Now, the common mistake that kids do is they take a look at each of these data sets and they comment about whether this has outliers or whether it's symmetric. But this is really not the comparison we want to make at all. Express. I don't want to, in fact, it doesn't look there's much of a difference, but I don't want to compare these things as two independent groups. So I don't check those at all. I need to take a look at a difference list. So in my calculator, I need to create the difference list, difference, and I'm going to put in an equation. I want to take the regular minus the express. So I can click vars, regular, minus vars, express, or you could just type them in, or you could do column A minus column B. So as you can see here, the express lane was 5 seconds faster. Here, the express lane was 246 seconds faster. And here, they had a negative 46. That meant that the regular lane was actually faster than the express. Okay? So we got some variability here. But that's the list I want to look at. I need to know if my differences have outliers or skewness to it. So here's the one plot of my differences. By the way, I'm testing to see if the difference is 0. You can see I had 4 points that were under 0 seconds, so where the regular line was faster, but most of my points are up here, and it looks like the average, on average, it looks like we have a positive average. So I'm wondering if that's significant. Is the average of this kind of significantly different for 0 so that I can conclude that the express lane really is faster in the population? Okay, so this looks pretty good. I don't see any outliers or skewness. You could look at, strong skewness. I would probably do a box plot. I do see some skewness, but there's no outliers and it's not too strong. So I'm going to say it passes. So I do a little plot of the data set, and I say the sample differences are approximately symmetric with no outliers. I've kind of changed my wording on this. I like to say there are no outliers nor strong skew. I like saying there's no strong skew better than saying it's approximately symmetric, because approximately symmetric is kind of a tough pill to swallow. That I don't need symmetry. I just want to make sure there's no strong outliers or strong skewness. So therefore, the sampling distribution of D bar is approximately normal. Again, I keep saying it, but let's just skip that so we don't lose points on the test. And now we're going to actually run the test. This is a paired t-test for mu D, or you could just call it a paired t-test, or you could call it a one sample t-test on the differences. I just prefer a paired t-test. Degrees of freedom is 15 minus 1. There was 15 in the sample, so 15 minus 1 is 14. Here's our formula. We're at the stage of this game where we don't need to put the formula down, but there it is in all its glory. And I actually found these numbers and plugged them in, but I'm just going to use a calculator to do this, okay? So let's calculate the test statistic, the degrees of freedom, and the p-value with the calculator. So I am going to go to my home page, and now I'm back to chapter 8 or whatever it is. I need to run a statistics, stat test. I need to run a one sample t-test, because a one sample t-test is how you do the mechanics of the paired t-test. And I have the raw data in my difference list. So I'm wondering if the differences are 0. My data is in the differences. And I'm wondering if the true mean of the differences is greater than 0. So I got my one-tailed test. My test statistic is 1.97. My p-value is 0.035, and my degrees of freedom is 14. Test statistic, t equals. Obtain a p-value, p-value equals. Now let's do our conclusion. I'm going to compare the p-value to the alpha value. Explicitly do this, or you will lose a point on the AP test, guaranteed. Statistical conclusion is to reject the null. So we do have convincing evidence that the true mean, I'm taking this from my p step, that the true mean of the blah, 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 that the true mean of the differences in times, regular minus express, at all possible times at this store is, word in terms of the the parameter is greater than 0, is greater than 0. Therefore, it does look like the express line is faster on average. Okay? All right, so we're going to do another one. Super. I'm going to do another video.